Welcome back after lunch. This is the final track of Uppsala. So well done for going the distance and making it this far. My name is David Pearce. I'm the session chair for this final session. Just a few little announcements first. Hopefully everyone has used the Slido system now. We will be using Slido to take anonymous questions from the audience, and then I will go through some of them at the end. The website is sli.do. Slido, and then you use Uppsala 18 as the session key to log in and go to Studio 2. Cool. So first up, we have verified three-way program merge, and Marcelo is here, and he's going to be giving us a talk. Cool. Over to you.
All right. Okay, everyone can hear me? Thank you. I am Marcelo, and this is joint work with Ishildi League at UT Austin and Shuvenu Nairi at Microsoft Research. I tried to make the slides a little bit up so that people don't have to be swerving to take a look at it. I hope it was a little bit successful. So I'll be talking about three-way program merges and verification of them. So let's just quickly recap what a three-way merge really is. So the context is quite simple. There's a group of people working on a project, and they're using some version control system to keep track of the changes across the project, across time. So let's just consider that we have one file in this project, and the contents of this file is just 1 + 1 = 3. Okay? So this is what we call the base. And then the usual suspects, Alice and Bob, take this file, and they make some modifications to it. So Alice changes it to 1 + 1 = 2. And Bob changes to 1 + 2 = 3. So pretty simple. So then the problem that we have is that we have 3 versions of the same file. So we need to somehow merge the changes that Alice and Bob did into the new state of the file that is common across the group. So this is what we call the merge. And so if you use Git, you probably use git merge at some point in your life. And what git merge is going to do is going to have a strategy which is called a textual merge. So it's going to line up the 3 files, and it's going to consider a line-by-line comparison of them in the sense that it's going to start by saying, OK, give me all the common parts of these 3 files. It's going to figure out that it's the first, second, and fourth line. And then it will try to incorporate the changes from the variants. So it will try to say, OK, what is Alice doing? So she's changing the last line and putting a 2. So let's put that into the merge. And Bob is putting a 2 in the third line. Let's try to put that. Right? So in the end result, what you get is 1 + 2 = 2. So this is probably not what you would like to have, but this is basically what's happening, and it's expected because it's a strategy that the textual merge is doing. So now when you start looking at the contents of these files, in particular when you go into code, subtle things can start happening, right? And here I just want to quickly credit Jim Laris for this nice example. So we have a method in Java. So you just get an object O, and then you check for a null check. If that's the case, you return. Otherwise, you call bar. You get the contents, the result of bar, and you only add it you only put it into O if again O is different than null. So what is Alice doing? Alice is checking. Okay, we have 2 null checks here. I'm going to remove the first one because that's okay. Bob is saying, well, I have 2 null checks here, and I know that once I reach bar, the method call to bar, then I know that O is different than null, so I'm going to remove the second one. When you ask then your automated merge tool to do the changes of Alice and Bob, you get this program, right? So you just get O, you call bar, you get it into a variable K, and then you put it. So it's pretty cool. And then what happens? You start at some point. It's in the process. You see, oh, I now have a null pointer exception, and Alice and Bob are pissed, and your manager is coming and saying, what happened? And then you're like, oh, it was the automated tool that did this, right? So it was, blame the algorithm, don't blame me, I'm doing everything okay. So this is kind of what we set out to fix. So this is, in our opinion, a painful and frequent problem. So someone say that this go-to-fail vulnerability back in 2014 was potentially caused by an automated merge that created this vulnerability. So when we start looking at the GitHub data set for commits, we start looking at, okay, is it the case that people are fixing bugs that are coming from automated merges, and we found thousands of them. We have manually inspected hundreds, and this seems to be the case. And people have already started looking at, okay, what happens when you have textual merges that are going through, but then, does it go through, does it mean that everything is okay? And then you figure out, no, doesn't mean that everything is okay, right? Because your build can fail, and then your test can fail, and even when your tests are passing, what guarantees do you have out of these strategies? So this is not exclusive to textual merge algorithms. So the limitations of textual merges have been studied for a long time, and people have tried to do specific so-called structure-aware merges for code, but they don't really give you these semantic guarantees that you are looking for. And in fact, our work is really inspired by work about 30 years ago. Susan Horowitz and Tom Rapps had studied like this program integration, and then we decided, okay, 30 years is a good time to pick it up. So here we are today. So in their problem, they are solving the synthesis. So they are trying to come up with a merge that is semantic aware. So what we do in the paper and this work is to tackle the verification problem. So given one of these merges, we want to prove that there is no semantic conflict with respect to the changes that we introduce in the variants. So what we mean by this semantic conflict freedom? So let's take the 4 versions of the programs. So we have the base, Alice, Bob, and merge, and we consider some output of interest, some observables that we care about. And so each program is going to output an array of observables, and so we have this matrix, and so we say that the merge is semantic conflict free. There is no semantic conflict if for all the rows, if one of the variants has modified the value, then this modification has to be present in the merge. Okay? So otherwise, it basically means that the base and the variants agree on the value that it's outputting, so the merge also has to agree with it. So this is basically what it means. So if you were doing some sort of runtime monitoring, let's do a couple of examples, right? So if I see 1, 1, 1, 1, then I know that I'm okay because they're all the same, so nothing has changed. If I see 2, 1, 2, 1, so this means that Alice has changed the value of the base. Bob agrees with the base, so Bob has not made any modification, so the merge can only choose one value, which is the one that Alice modified. Now if I see 3, 3, 3, 4, now I have a problem because essentially I have a merge is introducing some unwanted behavior. So there's something that is coming out of thin air, apparently, So this is a problem for us, like in the null dereference. It can also be the case that one of the changes, so either the change of Alice or Bob, is not incorporated into the merge. So we also want to fix this, right? Because we want all the changes that the developers performed over the base, we want them to be in the merge somehow. So this is the idea of what the property we want to verify. And as you can sort of see, it's a relational property, right? So you're taking 4 programs, and you're trying to prove a property over these 4 programs. So relational verification, the first thing you can try to do is you can try to take these 4 programs, you sequentially compose them, you give it to off-the-shelf verifier, and you say, is it good enough or not? So this technique called self-composition, we know that it doesn't work in practice. So in our approach, we decided to first try to figure out what's a suitable representation for tackling this problem from the verification perspective. So what we do, we start by taking these 4 programs, we perform a 4-way AST diff, and this gives us a shared program, which is this green one with holes, and then we have these 4 edit scripts which represent the changes that happen, the differences between these 4 variants. And after that, we have a tailored verification technique that receives this shared program and the edit scripts, and it's going to verify semantic conflict freedom. So some details about the pipeline. So in the first step, as I said, we have this 4-way AST diffing. We are considering differences at the statement level. And a feature of our algorithm is to be able to reuse out-of-the-box 2-way AST diffs. These edit scripts are really conceptually just a map from holes to statements. And the natural key property that we want is that if I apply an edit script to a shared program with holes, I get the original program back. So let's look at a little more complex example. So let's say we have the contents of a method where these blue variables are class variables. So what this method is doing is first compute some value based on some list. Then we have a queue, which we are going over, and we take an element. So we take an element of the queue, we compare it with the element we previously computed. If that's the case, if it's greater, then we are going to increment some counter. Then we exit the loop. Otherwise, we remove an element of the queue. We do some debugging, and we increment some local counter, right? So it's not something extremely fancy. So what is Alice doing? Alice is coming and saying, yeah, actually, I just want to debug if the current value I got from the queue is equal to the value I computed in the beginning of the method, right? That's the only thing that Alice is doing. And what Bob is doing is found this increment to the counter suspicious, so he's moving it from inside of the conditional in the loop to outside of the loop. So that's the change that Bob did. And in the merge, essentially what we do is the merge is just, a textual merge is going to give you the changes that both of Alice and Bob performed. So we take these 4 programs, and after we do the 4-way AST diffing, we come up with this program, this shared program with holes, where the first and the third one are about this move from the counter of the inside of the conditional to outside of the loop, and the second one is about the addition of the conditional on the debug. Okay, so if you want to kind of see the details on the algorithm, just you can check the paper or come talk with us after the talk. So this is the beginning. So this is what we receive, the verifier receives. And then what we do in the verification is to compute a relational postcondition. And this is a combination of standard technique of verification condition generation on sequential programs with product construction. And what that's going to produce, it's going to produce as a formula, which we call the relational postcondition. And then we're going to call Z3 to ask whether this relational postcondition implies semantic conflict freedom. And then we get a yes or no. So there are tricky ideas in our verifier. The first one is to summarize the shared code using uninterpreted functions and data dependency analysis. The second one is for the host to do relational reasoning about the differences using a 4-way product program. And for the loops, we realize that, in fact, the inductive invariant that we need are simple in the sense that it's just a conjunction of predicates between variables from different versions. Okay? So let me just give you the gist of the technique in an example. So what we start with the shared program with holes. We say that the lists, the initial values of the inputs, which are the class variables, are the same. Then we are going to look at the shared program, and we're going to abstract it. So we're going to say that I is going to be equal to some uninterpreted function because there's no data dependency. But in the case of val, we know that the value of val, it depends on the contents of the list. So we are going to say that val is equal to some other interpreted function that receives this list as input. And then in the case of the loops, we know that we have a hole there, so it's not so trivial. Under the hood, what we are doing is we are taking these 4 different loops, and we are fusing them using our product construction. But essentially, the invariant that we need is quite simple. So we just take that the queues are the same after we exit the loop, that this counter, the I, is also the same. And now we know that from this relational reasoning that only what we need to figure out is that the counter of O, the original counter, and the counter of A is the same. And this debug part, we actually don't care to prove semantic conflict freedom. So the product construction rules are detailed in the paper. And finally, when we exit the loop, we just need to figure out again that the counter of B is equal to the counter of M. So if we take this formula and if we feed it to Z3 and we say, OK, does this formula imply semantic conflict freedom? If I care about list, queue, and counter, we get back that this is true. So some details on the implementation. So we've implemented a prototype for verifying semantic conflict freedom for Java. The source code is available. And so what is the input of the tool? It receives 4 Java classes. The first thing it does is does an AST diffing at the class level to identify the methods that have been modified. Then we compute for each method the relational postcondition using this data dependency analysis and the relational loop invariant generation I explained. And as I said, we use Z3 as a backend solver. So we did 3 experiments to assess to evaluate SafeMerge. The first one is, can we find or can we prove semantic conflict freedom over programs that come from real data, from GitHub? In the second one, we try to figure out patterns from the literature where we know that textual merges like kdiff3 are going to produce erroneous or buggy merges. Can we find those bugs? And in the third one, we are wanting to validate our design decisions about, does this representation is suitable, and does this data dependency analysis really makes a big difference? So I'm only going to talk about the first experiment. The second and the third, you have details in the paper. I just want to say that we figure out that indeed the specialized product construction that we have and the abstraction that we are able to do with the data dependency are key to scale with respect to the program size. So it's really about just scaling with respect to the differences and not the program size. So how do we get the data from GitHub? So we crawled the projects, so the history of projects. So the first thing we do is to get, for each merge, we get the for commits. So that's basically just running these two commands. And then for each merge candidate, so for each base and two variants, we are going to replicate exactly the work that Git is doing. And we parse the output to find out which files are modified by both variants. So this gives us basically the files that were modified in both variants. And now we have to essentially figure out, OK, does this even make sense to look at these 4 files? What we do is we do, again, this 4-way AST diffing. And now we find methods which were modified in the 4 versions. And then we have to do some additional filtering to figure out, does this make sense to send to the verifier? So in the end, what we came up with was 52 merge scenarios from 9 repositories. As I said, we compared with kdiff3, which is an automated textual merge tool. The runtimes are very reasonable. So it was up to 4.5 seconds with an average of 0.5 seconds. So there's no big alarm that this will never be able to go into production. And so in terms of results, I think this table kind of nicely summarizes it. So out of the 52, we're able to verify, the SafeMerge is able to verify semantic conflict freedom in 39 cases. Out of these 39, 33 are actually the same thing we would get with kdiff3. So kdiff3 is passing. So we are able to verify that the textual merge is semantic conflict free. There are other cases. In these 6 other cases, what happens is that we have a textual conflict. So it means that there was some manual intervention happening. But we're able to verify that this manual intervention still satisfies the semantic conflict freedom. More interestingly, we have 13 cases where we do have a semantic conflict. So here, 8 of them are cases where you also have a textual conflict. So this could be for a variety of reasons. It could actually be a bug from 2 developers that have made some changes which are incompatible, and that does not satisfy semantic conflict freedom. But more interesting, we have 5 cases where kdiff3 is going through. So we get a merge out of it, and we are actually saying that there is a conflict. So out of these 13, we know that 2 of them are FPs because of abstraction, the type of modeling we do with collections. But in 3 cases, in these 3 cases out of 5, actually it could be the case that we have found a bug coming from these textual merges. So to conclude, textual and AST-based merges can introduce subtle conflicts. We use relational verification to ensure the merges are semantic conflict-free. This is, I believe, an excellent playground for formal verification. So in particular, we don't really rely on the developers. We sort of just use this semantic conflict freedom specification. There is a huge data set of examples nowadays because you can just crawl GitHub as much as you want to get some more examples. As I said, the scalability is kind of interesting to work on this problem from a scalability perspective because the verification seems to be sensitive to the differences and not to the program size. So if you have a good way of doing AST diffing, you can actually scale this technique to arbitrarily large programs. And moreover, in relational verification, the usual problem is always to come up with the right inductive invariants. But it seems that for this particular problem, these relational invariants are often not program dependent. So there is some hope for full automation and to put these sort of techniques into real development processes. So we developed this SafeMerge, and we tried to show that it can potentially be applicable in real-world scenarios. And for future work, if you guys are looking for a PhD, just pick one topic out of this, and don't let this problem go 30 years without continuation. And I think a very nice problem to work nowadays is really this semantic aware merge synthesis. So that's it. Thank you.
Okay, right. So we've got time for a few questions. Jonathan.
Yes. In your study, you looked at just one file, the changes in one file, but semantic merge problems could happen in changes across two files, right?
Right.
So I was wondering if your technique could be applicable, if you had anything to say about that.
Yeah. So that's a good question, and it's like a good I think a good point of the limitations of the current approach that you're looking at something localized even at the method level almost, and not taking changes that go across files or modules. So I think it's a nice problem to work on. So please.
Okay, so next I'll ask a question in Slido. So this is an anonymous question. The question is, why is it important to address these issues with n-way merge rather than just staggering them into two-way merges and forcing a user to pull first?
Right. I think that even when you just do a two-way merge, I think you still have the problem of, I think the problem becomes even more harder because you start stacking all these differences that are happening, and you don't really figure out exactly what are the potential problems that you can have. You don't know exactly what's the base, what was concurrently modified. So you could reduce it to two-way merge, but I think this nice compositionality that we have of saying, okay, I have one single version, I have multiple people working on it, can I take all these changes and put them into a nice new common state? I think it could be applicable. I would go the other way around. I would say, okay, why just three or four-way merge? Why don't you go for multiple stacking or sort of transactions? Yes, it really gives you more information.
So I really like this work, especially because it's taking on an old challenge and big. So one question is the theorem prover, is it sound and complete? So like when I see an X, does it really mean there is a merge problem? And when I see a tick, is it guaranteed to be safe? I mean, I think the tick is okay. The X, does it really mean there's a merge problem?
Right. So when we say that we have FPs, right? So it's not going to be complete, right? Because otherwise you would never have false positives. But if we say that it's semantically conflict-free, then based on the specification that we have, we are able to prove that it's sound. I guess one implicit question is, does it mean that this notion of semantic conflict freedom is the right one from a developer's perspective? I think that could be argued, but the technique is not really focused on this particular. You could tweak that particular property. I hope.
Yeah. So when you are automating multiple merge, how do you actually explain to a user what happened in the automated resolution process? Because the user can be more confused when there are conflicts. You are resolved like silently, right?
Right. Well, we're not doing anything with the merge. We're just taking a candidate merge, right? So the only thing we have to explain is this merge may have some problem that you are not aware of. So we are not looking on any synthesis problem, right?
I see. Thanks.
Okay, I think that's unfortunately what we've got time for today.
Okay, thank you. Yeah.